Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away.
46.56 degrees.
Good to
Well,
go.
thank you. I have a few questions to get started, and I have to say I'm a numbers girl, and
Glad to hear it.
not to that degree.
Oh, me neither.
No, but I have a thing I can do is columns in my head as quick as somebody can do the calculator. So my friends would always play that little game with me. I'm getting older. It's not as quick as it used to be, but it is a fun thing. And so my question was, why did they say that some of his theories were not correct?
Because they weren't.
So they...
Yeah,
Okay, I'm a little confused. That's a part of that where I went, well,
Yeah.
if he's one of the
in
greatest...
fact, they had one of the
mathematics-
most famous examples was actually in there where he had a formula that was going to estimate the number of primes,
Yes.
and he was wrong. And then Littlewood actually came up with something called Littlewood's number that said there is this number, which is way too big to calculate, but there is this number such that the thing flips. It doesn't estimate on the large size, it estimates on the small size. And in fact, it keeps going back and forth. And this is one of the issues, and it gets behind what Ramanujan was doing. And I'm going to mispronounce his name as well. But anyway, it gets behind what he's doing because he literally was seeing things. He had these things came to him.
Like
And
visions. Yeah.
to sort of understand sort of what's going on, you really have to go back into his early days. He's growing up in this small village in India, and he gets home, and he's mathematically very gifted. And his mother, by the way, was a sort of a tiger mum. She was absolutely pushing him. She said, "You're brilliant, we're going to do this, we're going to do this." And so she was, and he actually became fairly well known. He wasn't a complete unknown person.
In India.
In India, he was published in India, but he actually, he wanted to be known to the world. And so he was very interested in getting published. Actually, what really happened was, because he wanted to be published, he started writing, and he did get help from the British. He started writing to academics in England, saying he wanted them to help him getting published. He didn't want to go to England. He wanted to stay where he was. He was a Tamil. They couldn't cross the sea. That was his life. He certainly didn't want to go there. He wanted to be published. That was his goal. But when Hardy saw this stuff and couldn't figure it out, Hardy wanted him over there. He said, "We have to get this guy over here." So a colleague at Cambridge, Professor Neville, mathematician, was about to go on a tour of India to give some lectures. So Hardy asked Neville, "Seek out this guy and persuade him to come to England. We have to have him to England." So that was what led him to come to England. But to understand the background, and I said beforehand that mathematicians don't really know how he did it. In a meta sense, we do. What happened, when he was young, he got hold of a copy of an English book, which was a primer for university, high school leavers and university students in England, with many formulas. It was almost all of the known formulas of mathematics at the time, at least in number theory, without proofs. So he's given this huge array of formulas. He hasn't got a tutor, he hasn't got a teacher. He has to figure out what those formulas mean. Now, in his mind, he put together a structure, because mathematicians don't work with formulas. Mathematicians don't work with formulas any more than musicians work with musical notation. The musical notation is just the code to create the music inside your head. That's what mathematical notation does. It's the code that you create the symphony in your head. Most of us, when we create that symphony, we are guided by teachers and professors, and we create the same kind of symphony that others do. So, because we're taught that way. He didn't have that. All he had was the answers. He had to create his own symphony that matched these hundreds and hundreds of formulas. What happened was, in his head, he created this landscape, this symphony, this world, that in every single detail matched what he'd seen in that book. But what we clearly know now is his landscape wasn't ours. That was why when he was doing what we do, which is we see the symbols, it evokes this landscape, we look at the landscape, we give the answers, and you convert it back to symbols. And we can understand that. That's why I said I can understand how Newton did what Newton did. I couldn't have done it, but Newton did. I can see how he did it. I can see how Archimedes did it. Because we have all been living, we're in the same cultural tradition, we're living in that same context that allows us to create the mathematics from the symbols. Ramanujan created his own world. It was unique to him. There's never been anybody else with that world. And the reason it was crucial that Hardy forced him to do, actually Hardy didn't force him to do proofs. What they did was Hardy talked with him and said, help me create a proof. Hardy created the proofs himself, but had to have Ramanujan there. It would have been crazy to ask Ramanujan to learn how to do proofs. He wouldn't have been able to, but he was able to converse. And so Ramanujan kept, it was a long, long conversation. It was absolutely crucial because, and this was also well portrayed in the movie, without proofs, you really do have intuitions. And one thing we know about mathematics, especially where the infinite comes in, is the intuitions are unbelievably misleading. And so when Ramanujan created this world, which was his oracle, that was his God, that was his oracle, that's how the answers came to him, because he was mentally living in that world, so these things appeared. So he creates all of these things, but in creating his original world, like every one of us, he has to take a mind that's finite, that's used to the finite, and extend it to the infinite. That inevitably goes wrong. And only proofs will tell you when it goes wrong, and you have to learn to accept proofs. So proofs are absolutely crucial. And it took a long time, apparently, for Ramanujan to appreciate that, because he'd never had to do that.
Because he'd never been taught how to use
Never been-
proofs
and
to
it didn't-
check his work. He never checked his work.
He never had his work checked. One of the things that's important in mathematics is, and every mathematician realises this, is it's impossible to recognise your own mistakes by the nature of the subject. You're in it, you think it, and you create this edifice, and you create this logical argument. A mathematician, sometimes you can recognise your own mistakes, but every single mathematician has had the experience where they are 100% convinced that they've got the proof right, and it's not right. It's just like that. Because it's not like in physics where you have the real world to compare it with. You could do an experiment. In mathematics, it's all inside your own head. And there's no checks until another mathematician tries to understand it. And the only way for two mathematicians to communicate is through proofs. And that's when the rubber hits the road. So there was that clear tension, but it's absolutely essential, and it's true today for all mathematicians. Like any mathematician, I get sent proofs by people that are absolutely convinced they're correct, and they're not. And I have incredible sympathy, because unless you've lived in that world and got used to the fact, and I've gone through this many times, that what you thought last night was absolutely correct, isn't going to stand up to the cold light of dawn. Happens all the time. We learn to live with that, but many people don't, and it's a difficult pill to swallow. And it was clearly difficult for Ramanujan to swallow, and that was also shown well in the movie.
But it seems like in the movie he got really close when they were saying like 0.04%.
That was the formula for the partition, yes.
Yeah.
Yes.
So does that mean his formula was right?
It was actually, if you look, there was a sequence when there was a drawing of a circle on the board, and he said, Cauchy's theorem helps us, and he said, as n goes to infinity, the error goes to zero. That's a proof. That means that formula is absolutely correct as an asymptotic formula. In number theory, what you're saying is, what happens when the numbers get bigger and bigger and bigger? Well, you never end that process. So you look for asymptotic solutions that you have a formula that if it's p of 100, it's right within a few hundredths of a decimal place or something. If it's p of 200, it's more accurate. The bigger you get, the smaller the error gets. And that's typical of number theory, because what number theory does is says that all numbers having property A have property B. That's essentially what number theory is. Well, you can't do that by looking at all the numbers, because there are infinitely many of them. So you come up with a formula and show that the error of that formula, and there has to be an error because you're looking at an analytic formula. Questions in number theory tend to have exact answers because they're about numbers, and they have numbers. When you do things, have answers. But the formulas are analytic formulas. That means they're involving calculus. So these formulas give approximate answers to questions that in principle have exact answers. Once your error is less than 1, it's the right answer, because it can only be, if you say something, 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 and the formula gives you 1.1, or let's assume the formula gives you 10.1. Well, the nearest number to 10.1, the nearest whole number, is 10. So what the formula says is the answer is 10. The formula had an error, but you can ignore it.
There's no absolute.
There's no absolute except in the limit when you go to infinity. And so it comes down to, the proof comes down to show that the error term tends to 0. Then that is absolutely a solution. And it can help you with understanding black holes, as they said at the end. Although that's really kind of mysterious. That's really mysterious.
Well, and it seems like with coding, with everything else, the mathematics is what gives you the basis from which you launch.
It's sitting there in your iPhone. The reason the FBI wants to get inside Apple is that Apple has all of this stuff based on Hardy and Littlewood's work, and that's what makes your iPhone secure, and the FBI hates it. They need to find their own Ramanujan, and I'll bet they're looking.
And so there's nobody that's ever been like him before?
Actually, there never will be, because to do that, you would have to put someone in isolation and let them do what he did, but they would then end up in a different world. That is a method. This has been recorded, so I'm not advocating we do this, but in principle, this is a thought experiment. Mathematicians do counterfactual arguments all the time. In principle, if you isolated smart people at a very early age and give them lots of books without any proofs, you would create a group of geniuses that could do remarkable Ramanujan and things like that. Because, he was a human being. I mean, he's not God, he's a human being, and that was also in the movie. And human beings, to me, what that shows is that the human brain is just a remarkable thing, because it can create these worlds that are actually useful. I mean, people create their own worlds, and sometimes we call them crazy with justification. Sometimes it's hard to see whether they are or not. But in the case of a mathematician, there is an ultimate check, in that if those results cash out, if you can go to a Major McMahon and say, you calculate 200 on a paper, and my formula will check it. If you can put it to that kind of a test, then whatever that person has created in their mind is valuable and useful. And Ramanujan was Ramanujan, and in principle, if another person was raised the same way and had the same experiences, they would come up with another mental model that would give us different mathematics.
So mathematics is still constantly changing.
The same thing was true of Riemann in the last century. Riemann, who produced something called the Riemann hypothesis and various other things, Riemann was a mathematician who came up with some amazing conjectures, some amazing ideas. Now, in his case, because he was in Germany, he was part of the Western tradition, we can sort of get inside his mind and we can understand how he did it. But it's still a remarkable feat that he was able to do things that have taken many years to prove.
So the one scene when he was hallucinating, and in his hallucinations he could see the numbers literally popping off the skin, was really in reality what he lived with every day and every moment.
I've had an experience of influenza where the same things happened. Seriously, you feel as though numbers are crawling over you, some are friendly, I've had that experience with influenza where you wake up and you're in this weird world and you literally do things like numbers coursing through you. I've had that experience. I suspect many mathematicians have as well.
What's your number?
Only my friends have my number. You've got to invite me to meet Dev Patel and then I'll give you my number.
Hey, I want to meet him too. We're right there together on this one. Tucker, you have anything you want to add to this interesting movie? And
I've now seen this movie 3 times, and I'm astounded at the effect it has on me. My hero growing up was Mr. Spock. I have certain pride in not getting emotional, and yet this movie pushes my buttons. I don't get it. I do love it, though. Something else that I've got to say about why this particular viewing was so moving is because of this theater and this audience. Thank you so much for this experience. Okay, now, regarding the hallucinations during the fever, Keith was kind enough to point out another one earlier on where not the numbers crawling on the skin, but I thought, were they dropping bombs from dirigibles in the First World War? And I thought, how ineffective, how do you... Yeah. And apparently, I believe, Keith, you're arguing that, no, this was
Certainly not in Cambridge.
Yes.
Not in Cambridge.
Yes. Not one of the most important mathematical insights from this movie, but I do want to know where fantasy and reality separate here.
And if there's such a thing. I think I tell you, this is very interesting and fascinating. I want to open it up to the audience, though, for some questions for our illustrious guests here. And also, just remember, butt out, please. Okay, any question? We got one right in the back. Go ahead. And if you talk into the mic, that helps us.
For a very old...
Up close to your mouth, please.
For a very old Stanford English major, could you explain what the hell he was talking about? What is partition theory?
Oh, this is one of those movies where you...
In lay terms.
Yeah, it's actually one of those movies where you need to see it twice because it was explained in there. It is just... Everyone knows about prime numbers, I hope. And prime numbers are the building blocks of numbers for multiplication. Every whole number can be broken up into primes in a unique fashion. Okay. You can ask a similar question in terms of addition. Start with a whole number. How can you break it up in terms of addition? Well, you don't get uniqueness. You get many, many different ways of doing it. The example in the movie was if you try to look at 4, you can express it as a sum of integers in 5 different ways. And you can work it out for 5, you can work it out for 6. It takes a while. You have to get some systematic way, but you can just start listing them. Then the question is, what about big numbers like 100, 200? In fact, McMahon in there, he did calculate it, the real person did calculate it for 100, calculate it for 200. The question that the mathematicians asked was, and this was the so-called partition question, the partition formula, is there a single formula that without having to take a number and split it up into all of its different ways will tell you how many ways you can do that? Now, in the case of prime numbers with multiplication, there was an analogous result called the prime number theorem that gave you a formula, and it was in the last century. There's a formula which tells you within an acceptable degree of approximation how many primes there are up to a certain point. So in the case of primes, which is the complicated stuff, because it's arithmetic and so forth, is multiplication. So in the case of primes, there is a formula that tells you how the primes go. It was frustrating that with the much simpler case of addition, splitting a number in terms of addition, there was no known formula. So the question is just how many ways can you split a number in terms of addition? The difficult thing, and checking any one case was just a matter of calculation, but coming up with a formula was, as they said correctly in the movie, regarded as absolutely impossible until Ramanujan came along and did it. Now, once Ramanujan, in fact, they really did get the mathematics right, because Ken Ono is one of the people who spent his career going through Ramanujan's notebooks. Ken Ono was the mathematician who was advising on the thing. He actually did say, it was said in the movie, right, that shown in the movie, that when Ramanujan put the formula in front of Hardy, originally Hardy didn't look at it, and then later on he did, and he said, he's got it. Because one of the things about formulas like that is, if you're in that domain, you can glance at it and you say, this has to be right, as an instinct. Because once the formula's written, that can very often, in fact usually, provide the link between those mental minds, in that case, of Ramanujan and Hardy. Their landscapes were different, because we have no idea what Ramanujan's landscape looked like. Neither did he. He just said, God tells me, this goddess tells me what's going on. But once you have the formula, that's the link. That links Ramanujan's mind to Hardy's mind. The only question then was, Hardy needed to develop a proof, or to get Ramanujan to work with him to develop a proof, so that Hardy could get enough insight into Ramanujan's world to see what Ramanujan was talking about.
Interesting. Let's go right here in the middle of this gentleman. Malin, can you come on down right there? And then we'll get to you next. Thank you. And if you can hold it real close and talk into it.
I wonder if you could describe some of the other breakthroughs in mathematical work of him. The film only covered a few.
Actually, the two Lost Notebooks, the Lost Notebook and the early notebooks, those have still been gone through. George Andrews, together with Ken Ono, have been spending most of their career pouring through that and coming up with one result after another result. There's still a ton of stuff in there that's not known. There's a whole thing called Mach theta functions, which does this, that, and the other. There's an endless. I mean, by the way, this is not my domain, and so I'm just, I'm about 2 inches ahead of you in terms of knowing what I'm talking about here. But there's an enormous range of things. They're almost all in analytical number theory, which means you're applying methods of calculus to understand questions about the whole number. That's the discipline known as, there's two kinds of number theory, there's several actually, but there's the two main ones are algebraic number theory, which uses methods of algebra, and then there's analytic number theory, which uses methods of calculus to look at these questions about whole numbers. Ramanujan was in that domain, which was an interesting domain because it was based on understanding the world through calculus. So he was using the tradition of Newton to get into that. And rather than mention, there's a bunch of names one could mention, but the way to think of it is that what Ramanujan did in those notebooks was take this method of calculus and apply it one after another to answer questions about number theory. To some extent, that sort of explains the domain he was in. Because he was using this English book of formulas, which was basically formulas of calculus, his only view of mathematics and number theory was based on calculus, which means continuums, continuity, landscapes, sort of smooth objects. So his view of the numbers was heavily in terms of landscapes. And landscapes is a little bit of an understatement because who knows exactly what it was. But he had some hyper landscape model in his mind that literally did allow him to say this is the case. Because imagine you're in a real landscape and you're walking around and you're talking on a cell phone to someone and that person says, what do you see? You could then quickly look for, so I'm seeing this, I'm seeing that, because it's there. Well, that was what he was doing in his mind in this landscape of mathematics. So he literally would see, oh yes, I've seen that. You would also have the experience, you wake up the next morning and suddenly you realise that three things you'd seen the day before were actually different aspects of the same thing. So you get your phone out again and say, hey, I've just realised that those three things were connected. You had simply observed it and thought about it. Well, that's what he was almost certainly doing in his mind, because he was in this landscape that he'd created over many years in his early life, and he was just living in that landscape.
Interesting. Can we get this question right there, Malin?
I was wondering if there's any study of who influenced Ramanujan, and I'm particularly interested in Cantor, and maybe you can discuss for the audience who Cantor was and why that's important. I'm not an expert, but I would doubt very much that Cantor was an influence. He may not have even known about Cantor's work, because Cantor looks at infinity in a very different way. I would be prepared, I'm sure that Ken Ono or George Andrews would be able to give you a more definitive answer because they are the experts on Ramanujan. But based on my own knowledge of Ramanujan and the disciplines, I would think it was possible that Ramanujan would not have been able to even get his mind around what Cantor was doing. He clearly had the intellect to do it, but without the motivation, I doubt he would, because it's a completely different way of thinking about things. So my strong suspicion is he wasn't influenced by him. In fact, everything I know from the story of Ramanujan suggests that he wasn't really influenced by anyone except indirectly. And that was the strength, because if he'd been influenced by one of the greats, he would have been more like them. The reason I think we are completely mystified by how Ramanujan did these things is that there was no influence. He just had the human intellect applied to a domain where he had some points available from this book he read. That, I think, is the secret, and it was that isolation, I think, that made him so unique.
We're going to get a ladies' question. Come on down, Malin.
By the way, the same can probably be said of Poincaré, because Poincaré was very short-sighted, couldn't see what the teacher was putting on the board. So when Poincaré was a student, in his mind he created his own images, and it turned out, he was only slightly behind Einstein in coming up with relativity.
So do you think if he had been raised in the Western tradition, his work would not have been so startling?
I'm absolutely certain of that. Otherwise the thing, I'm like Hardy. I can't say he really was talking to God, because I have the same view as Hardy does. So the only answer I have is if he'd been raised in the Western tradition, he would not have been Ramanujan. So I have my own faith, and that's my faith in that one at least.
I've only got time for 2 more questions. I'm going to get this lady over here, and then we'll go back to you, sir. Sorry.
They did a point in the movie when he was talking to the council at Trinity of of scholars that from Newton onward, formulas in math were at the time considered invented and not discovered. Was it really that event that really helped bring that new concept into mathematics, that formulas are discovered now?
No, it wasn't a single event. It's been a general evolution, and it's actually an evolution that it's one of these things where every individual mathematician I know, and certainly for me, goes through a period as they develop where you reach a stage where you get this conviction that all of the formulas are out there waiting to be discovered. And there's a certain reason why that's the case to do with how the mind works, because we've got all sorts of evidence from cognitive neuroscience now to help piece a story together. But if you're a mathematician, you come to this period where you have a sense of discovery. But then as you get older and you start to think about it, you think, no, the only thing supporting this is the human mind. And so the fact that we have mathematics reflects the fact that the human minds, although they're all individual and different, have an enormous amount in common. And so there is a common domain. So most of us who are 50 years old or older in mathematics tend to say mathematics is a social construct. Anyone under 50, if they're still active in mathematics, says, rubbish, mathematics is something that's discovered. And you know you're getting old when you've gone from one to the other.
We'll finish up with this one last question and answer. And then we're going to have Keith and Tucker out in the lobby, and we'd love to get some comments from people and ask them questions. Yes, sir.
Does any of this touch on what Schroder's cat is? I mean, do we have any inkling that this led to string theory, etc., or is it just totally going the other way?
The simple answer is it's completely separate. The reality is, of course, there's a whole, all of these disciplines go through together. All the mathematicians, well, unless you're isolated like Ramanujan, you're influenced by everything else. You know, there was right at the end it said this work has been used to look at black holes, and it's actually known that there are strong connections between black holes and the structure of the prime numbers and so forth. Now, what that really reflects is that universities are places where mathematicians and physicists occasionally meet and talk and get drunk together and do all sorts of things. And these are smart people, and it's amazing how often you get slightly tipsy and you say, you know, that sounds like this, I'm not making this up, it sounds like this, it sounds like that. And you wake up the next morning and you think, you know, there's a little bit more to that. So the ideas from one part of the mathematics and physics in particular do this. The ideas ebb and flow. And you take an idea from one, you move it, and then you begin to push it. And sometimes it's just artifactual, there's no real content to it. But sometimes, and certainly in this case about black holes and one of other connections with physics, there are these tantalizing connections that we think, well, maybe the Riemann hypothesis does have something to do with the structure of the universe. In some sense it does, because the Riemann hypothesis is a fundamental question in mathematics to do with analytic number theory and the structure of very important numbers and functions. And physics is based on a mathematical view of the way. The physics is the world looked at through the mathematical lens. So in some sense, the mathematics and the physics will connect, because if you're a physicist, you're looking through a pair of mathematical spectacles, and that's going to influence what you can see. Whether there's something more than that, whether there is a real application in physics that depends upon something to do with the Riemann hypothesis, maybe that will never be the case. But the ideas mix together. And you know, any mathematician who says physics doesn't influence me, they just need to wake up and smell the roses.
I want to thank everybody for coming today. I want to thank our special guests, Dr. Devlin and also Tucker Hyatt from Wonderfest for being part of this. I would ask that if you want to stick around and ask them questions in the lobby, you do need to sign a little waiver form we have out there, because we are going to use your comments, or I will say Alfred P. Sloan Foundation may use your comments in part of their educational process. And don't forget, October 21st, Life Animated, the second in our Science on Screen. Thanks, everybody.